Hi once again. So we are studying analysis techniques in frequency domain. We have seen serial parallel equivalence elements and how we could use it in the analysis methods, and the source transformation also the same. And the general analysis techniques, we know there are three of them. One of the classical method, this one, you're going to write two any equations, two any unknowns. The number of equations are a bit many of those elements, equations. Any is the number of elements. So when the number of elements increases, to any also increases. So many equations that we have, not easy to solve. So to simplify this number of equations, or reduce the number of equations, we use the other two methods. One of them is node voltage method, the one that we are going to examine right now, and the other one is the mesh current method. Node voltage method, we have an example circuit here. We are going to examine the method on an example. This example a bit different from the previous classical method example. The difference is there is a dependent source in it. So when there is a dependent source in it, you've got to be a bit careful, just a bit careful. So where you should be careful, I will be explaining in details later on. And also we will be examining, you see the Proteus result of the same circuit, so you can compare your calculation results with the simulation results. So let's move to whiteboard now and escape from here. Come here, open board, and open board. Here. Now the circuit given to us is time domain circuit, which is this, isn't it? Time domain. And we are going to transfer this time domain circuit to a frequency domain circuit, or let's say in short, omega domain circuit. How we will do it, I will explain it right now. Change the color. So there is an independent voltage source here. We are in frequency domain. That means all the dependent sources are going to be sinusoidal functions. So this is one of the example of it. This time domain sinusoidal function is going to be transferred to phasor of this sinusoidal function in the frequency domain. What is the phasor of this element? Is Vs is equal 10 and e to the power 0. Why it is e to the power 0? Because the phasor of this sinusoidal function is 0. So therefore Vs is equal 10. The phasor of the independent voltage source is 10. For the resistors, definition relations, whether it is in frequency domain or omega domain, do not change. Therefore the 10 ohm, this 10 goes to 10 ohm here, and 20 ohm here, and that 50 ohm here. And also dependent sources, definition relations whether in frequency domain and time domain do not change. Therefore this is also transferred as it is to the frequency domain. But when you come to the inductors and capacitor, this is going to change. We're going to write the impedance of the inductor, impedance of these elements. For the inductor of the inductor is, impedance of an inductor is ZL J omega L. J omega is the radian frequency, angular frequency of the independent source, so that is omega. So that means omega is 100 times L. L is 100 millihenry. 100 milli 10 to the power minus 3. You end up with J10. So that's the impedance we wrote on the top of this inductor here. And the impedance of a capacitor is 1 over J omega C. So if you move that J upwards, that means multiply denominator and numerator by j, you're going to end up with minus j 1 over omega c 1. We already said omega is 100 and j is 100 microfarad. 100 micro is 10 to the power minus 6. So 4 zeros, 6 zeros minus, so you end up with, forgot that j, minus j 100. So impedance of the capacitor is minus 100J. You can always say that capacitor impedance's sign is always negative and inductor impedance's sign is always positive. Now what we're going to do next, we are going to write node voltage equations. We are going to start with Kirchhoff current law equation. Kirchhoff current law equation. So Kirchhoff current law equations are going to be written for all the nodes. If you compare the nodes now here, node 1, node 2, node 3, and this node I didn't mark it with a number here. The reason is these two elements are connected in serial, so I can replace those two elements with just one impedance, of which impedance value is 50 minus J100. Then one of the node disappeared, isn't it? So that means I'm going to write less number of equations. That's a good practice of serial connected element replacement. You've got to need to pay attention here. This is something that you cannot do in time domain. In time domain, you cannot replace those two elements with one element. But in frequency domain, you can replace those two elements impedance with just one element. So that is one of the advantage of the frequency domain. So after remind you all that, we are going to write the Kirchhoff current law equation for the first node. Before we start, the current reference of this independent voltage source is downwards. The reason is passive sign convention is known. So okay, what is this current? Is IS, let's say, IS, independent voltage source, current phasor, that is. That's why this is capital I. It's not time domain current. This is frequency domain current. And plus that current, that is 10 ohm resistor current. So I am going to write this 10 ohm resistor current in terms of node voltages because the method that we are using is not voltage method. How I am going to write it? You know the introduction to electric circuits, but I am going to repeat it once more here. So the current is coming out of the node, so the sign is going to be plus. And then we are going to write the voltage of this element in terms of node voltages. How I'm going to write it? The beginning of the arrow here is, beginning node of this arrow is VD1. The sign we already said plus. Beginning of the arrow VD1 node voltage minus the ending node voltage VD2. So that's the voltage of this element. If I divide this voltage to 10, I end up with this current of this element. So remind you what node voltage is. Node voltage is the voltage between a node and the ground. So ground here, assumed here, is this. So when I say end node voltage VD1 is the voltage between those two, so you can easily say that voltage is the same as this. But if you write this element node voltage, is not just one node voltage that you're going to use. It is the difference of those two node voltages. So there are two elements connected to that node, therefore there are two terms in the first equation here. So the second node Kirchhoff current law equation is this current. I'm going to repeat it here, but the sign is going to be negative because for this node this current is coming towards the node. So minus VD1 minus VD2 over 10 is the current of this element, and current of this element, since this is ground, VD2 over 20. Sign is positive because it is coming out of the node. So plus VD2 over 20 is that current. What about this current? So the sign is positive because it is coming out of the node. And the voltage of this element VD2 minus VD3, VD2 minus VD3 over 10J is this current, so inductor current. So there are three elements connected to that node, and I've got three terms in my equation, so A is equal to 0. So when you come to this third node, that's the final node, the sign of this inductor current is going to be negative because this arrow comes towards the node, minus VD2 minus VD3 over 10J is this current, and current of this element. Now we've got to stop here for a while because we faced now with a dependent source. So before go any further, write the definition relation of this element that stops you to make mistakes later on. How I am going to write the definition relation of this element? So look at the shape, this diamond shape. Because of that diamond shape, this is a dependent source. Because of the voltage reference given inside it, it is a dependent voltage source. So this dependent voltage source voltage depends on that current. That current is this element current. So it is current controlled dependent voltage source. So V, current controlled dependent voltage source, voltage is equal 5I. That's the definition relation. So in that definition relation, we don't see the current of this element. So this element has got current controlled voltage source current. This current is not seen in the definition relation. Now while in here we are writing Kirchhoff current law equation, so I'm going to write the current of this element. So according to passive sign convention, direction is downwards. So this current is going to be plus ICCVS. Now most of the students, they do mistake right now. Don't write this definition relation VCCVS or 5I here, because what you are writing is not the voltage but the current, isn't it? This is Kirchhoff current law equation. So that means while you are writing this equation for this element, you cannot use that definition relation at that moment. If you cannot use it, so you're going to use that current of this element. This also means that you are introducing a new unknown, because our unknowns in these node voltage methods are the node voltages. So we introduce a new unknown right now. What does this mean? Later on, we've got to write a supplementary equation because of this new unknown variable. Okay, we wrote this current. So what is left is this current. So we already said you can replace those two elements with just one this here. So if you consider the current direction downwards, so in terms of node voltages, what is this current? This node voltage between this node and ground is this impedance voltage. over this impedance gives this current. Direction is coming out of the node is plus, that's why the sign is plus. So VD3 over Z impedance, which is 50 minus J100 is equal to 0. So we have 3 nodes and we wrote 3 node voltage equations here. So if you write now the number of unknowns, there is one unknown, this was a new unknown came in, this is another unknown saying here, IS, we don't know that, and the other unknowns is VD1, VD2 and VD3. So altogether we've got 5 unknowns, but we've got 3 equations here. We've got to write 2 supplementary equations. How we are going to determine this supplementary equation is critical. The unknowns, the new unknowns you introduce, for each new unknown that we introduce, I am talking about these 2 new unknowns we introduce here, we are going to write supplementary equation for each of them. So for IS, how I am going to write the supplementary equation? The answer is simple. You are going to use definition relation of this element. This element is independent voltage source. Independent voltage source definition relation is here. So if you write this is not the proper supplementary equation. Why is that? Because this voltage is not in terms of node voltages. So you're going to transfer that Vs to node voltage easy. So this element voltage is the same as this node voltage since this is ground, isn't it? So that means VD1 minus 0 gives you this voltage. So don't write that minus 0, then V supplementary equation. First one, VD1 is equal to 10. So one of the supplementary equation is this. The second supplementary equation, look at the new unknown that we introduced in this equation is this one. So as I explained before, for this one I will be using the definition relation of this element, which is this, in order to write this supplementary equation. So let me write it here. Now be careful here. If you write this definition relation, it is not the supplementary equation. Why is that? Because the variables here are not the ones that I am expecting. Why is not? Because we are writing the node voltages. You've got to transfer these variables to node voltages. So this one and this one should be transferred to node voltages. When you do it, then it is a supplementary equation. How we are going to do it is easy. This element voltage is node voltage, isn't it? That VCCVS is VD3. Why VD3 minus something? Why it is not VD3 minus something? Because minus 0, isn't it? That's ground. This node is ground. VD3 minus 0 is the voltage of this element. So VD3 is equal to 5. So I need to replace that I with node voltages. So you see that I is written here, isn't it? That is I. Not this side, this is minus I is this one. So I'm going to replace that I here with this one. So 5 times VD1 minus VD2 over 10. So this is now supplementary equation. So this is supplementary equation. If you write this as a supplementary equation, it is not a proper supplementary equation. So you can get less score if you write this definition relation only. So now the number of equations are 5 and the number of unknowns that we are trying to calculate is 5, so there is a unique solution, no problem there. You might say that the problem is 5 equations, 5 unknowns, not easy to calculate, but don't worry that much, because if you examine these equations now, first of all, VD1 is equal to 10, that means you reduce the number of unknowns, isn't it? So this is solution. So 4 variables, 4 unknowns. In these 4 variables, 4 unknowns, one of the equation here, we've got IS. IS seen in this equation only, nowhere else. Therefore, this equation helps us to calculate that unknown, that IS. So I am going to consider this equation later on. This equation, for example, has got ICCVS. So this equation helps us to calculate this unknown. It is not seen any other equation. So I'm going to leave this one and this one later on to be used. So what is left is these two, isn't it? If you look at these two, we've got only the node voltages. So we know VD1 already, and in here I can write, if I VD now, so I can calculate VD3 in terms of VD2. So if you replace VD3 in here with this, you're going to end up with one equation, one unknown. So it's not really 5 unknowns, 5 equations. It is just one unknown, one equation. So easy to solve out. Let's do it now. So in here, if you multiply all this by 20, move that j upwards. So I can say that you can move that j upwards, saying that minus j, isn't it? And multiply all of those with 20, you're going to get 20, that means 2 times this, minus 2 VD, so sorry, not, this is the capital VD1, it should be, near Y capital, because it is phasor, isn't it? Minus VD1 plus 2 VD2. I multiply this with 20 and you end up with this 20, so plus VD2. So this is multiply with 20 gives you 2 minus 2j VD2 plus 2j VD3 is equal to 0. So this 5 and 10 is going, that means 1 over 2 VD1. VD1 already I know that it is 10, isn't it? 10 minus VD2. So that's minus 2 VD1. So okay, if let me write it once again. Minus 2 VD1. VD3, 3 times VD2 minus 2j VD2 plus 2j times this. So that is 0.5 multiplied with 2 makes it j, isn't it? I'm going to multiply j with those two. So that means 10j minus j VD2 is equal to 0. So what we've got here, VD1, which is 10, so that is 20, isn't it? So if you move it right to the side, this is 20 minus 10j is the right hand side. So I move this one and this one. VD2 case, so that is 3, isn't it? Minus 3j VD2. So 3 times 1 plus j VD2 is equal to this one. Okay. So from that VD2 is equal, if you put 10 parentheses, 10 2 minus j over 3 minus j. So if you're going to multiply both of them plus complex conjugate of this one, 1 plus j, and do the calculation, you're going to end up with a phasor. This phasor is going to be, come back to that, Prezi. Node voltage method here. So VD2, you're going to end up with this. Once you found that VD2, so you can use the definition relation, you can find that VD3. And from the first equation, you're going to find the IS because you already calculated VD2. It's going to be this one. And current controlled voltage source current is going to be calculated this third equation, because we already calculate VD2, VD3, so we can calculate that VICCVS. So it is this. So what we have done we have found 5 unknowns. These 5 unknowns, 3 of them is node voltages. The other 2 are the new unknowns that we introduced. For these new unknowns, we wrote the supplementary equation, but in the end we have found all these new unknowns has been calculated as well. Unknowns have been calculated as well here. So that is not the end of the analysis, because these are the variables, artificial variables. So our aim is to find out all the elements current and voltages. From this, since we know the node voltages, we can calculate all the elements voltages, and then use the definition relation, find all the elements currents. So these all done here. Just explain one of them. Once you found the phasor of a voltage, let's say this one, you can transfer it to time domain if the phasor is written in polar coordinate. So at the end of the calculation, the phasor that we are going to end up with is in Cartesian form. So you transfer this Cartesian form complex number to polar form. When you transfer it to polar form, it is easy to transfer your phasor to time domain sinusoidal function. How? The module or the magnitude of your complex number is going to come as a magnitude of your sinusoidal function. So 5.64 here, 5.64 here. Cos 100t is the same part of the independent source. We said we are trying to find out a particular solution in frequency domain. Particular solution is the solution in the form of the independent source. Independent source sinusoidal function, so cosine function, this is a cosine function. And this function frequency does not change for all the elements. So this 100t is going to be the same. And the phasor that you're going to end to the end of this sinusoidal function is the angle of your polar coordinate phasor. That is minus 18 here comes to here as an angular part of your sinusoidal function. So that is the end. Before, let's say it is end of the this video, we said if you do the simulation, this circuit in Protos, so you're going to end up with this node voltages here, and it has been chosen a capacitor current is yellow one here. So if you look at these result now, let's interpret that result. First of all, since the independent source is sinusoidal function, we know that the solution is going to be sinusoidal as well. The particular solution is going to be sinusoidal. The one that we calculated before here is the particular solution, but the one that you found here in Protos simulation is the general solution. That is the difference. So at the beginning there could be some changes. That explanation tells me because of the transient solution at the beginning, so the beginning part could be a bit different. But if you take your scale here, so that means that's time scale, that is 100 millisecond. If you make it 10 second, so this part is not going to be the same in detail, so you're going to see exactly particular solution, not the transient solution. So in general, what you can say here, that this blue one here is the independent voltage source, so 10 volts here and minus 10 volts here. And if you look at this is the one period of this independent voltage source, that's the period. So how are you going to check it with which is angular radian over second angular frequency? In Protos, you are saying the F frequency, not the angular frequency, the normal frequency. So this time, 1 over these times gives you the F. That means the normal frequency. Unit is Hertz. If you multiply that F with 2p, then it becomes omega, so you're going to end up 100. So you could do this check by the calculation that I just explained to you. That's one thing, the difference between Protos and the calculation in time in frequency domain. And the other thing that you are examining here, for all these other elements, if you look at the frequency, if you calculate the frequency, you're going to end up with the same as the independent voltage source. That means the frequency of these elements, frequency of the sinusoidal function of the elements do not change, and they are the same as the independent source frequency. What is changing is the magnitude. You see the magnitudes are different of these sinusoidal functions, and the angle is also changing. So that means phasor, isn't it? Phasor do not have the frequency in it. So the amplitude and the phase of the signals is changing. So how we can calculate the phase difference between two signals? Let's say this red and blue one. So you can calculate the phase difference. How you're going to calculate it is easy. So one period time is 360 degrees. So that means you can measure the period here for this blue one, for example. So that period in terms of time is represented by 360 degrees. So if you make a proportion saying that the time difference between these two peak values corresponding to what degree? So from that you can calculate the phase difference between two signals. That is one thing. The another thing that you've got to pay attention here is if you look at the let's say this red one, you can consider the yellow one as well. So the red one, the peak value here is lower than this one, isn't it? So that means that peak value is changing a bit. So the answer to that one, these peak changes, because of the transient solution, it is changing. If you change the scale here from 100 millisecond, let's say 10 second, you're going to see all these peak values are going to be the same because this is a particular solution. So the transient part affects these peak values as well, as seen here. So that's the end of this video then. Come to